Majority of motor skills require a person to perform with speed and accuracy combined. There are two types of speed accuracy skills: manual aiming skills and speed accuracy trade-off. Manual aiming skills involve hand movements to a target, requiring that the hand arrive at the target, but at a speed the performer determines. Manual aiming skills include putting a key in a keyhole, placing a pen in a pen holder, and threading a needle. Speed accuracy trade-off is defined as a characteristic of motor skill performance in which the speed at which a skill is performed is influenced by movement accuracy demands. The trade-off is that increasing speed yields decreasing accuracy, and vice versa. In other words, the accuracy requirements of the movement will influence the movement speed, and an emphasis on accuracy will reduce speed, while an emphasis on speed will reduce accuracy. Thus, we typically trade off speed for accuracy, and vice versa. Consider how this trade-off would occur in the example of a penalty kick in soccer. When a player tries to kick the ball at the fastest speed possible, the typical result is an inaccurate kick. Conversely, when the player emphasizes accuracy by trying to kick the ball to a small part of the goal, the result is often a ball kicked too slowly to make it in the goal. Evidence for a speed-accuracy trade-off in motor skill performance had become so common that a mathematical law was developed to predict movement speed, given specific accuracy characteristics. This law is called Fitts' law. Fitts' law is defined as a human performance law specifying the movement time for an aiming movement when the distance to move and the target size are known. The variables that predict the performance outcome are the distance to move and the target size. According to Fitts' law, if we know the spatial dimensions of these two variables, we can predict the movement time required to hit the target. Fitts' law applies to many skills. Research shows that when people perform manual aiming tasks, such as throwing darts at a target, reaching or grasping for containers of different sizes, playing a piano, etc., their actions demonstrate movement time characteristics predicted by Fitts' law. Three prominent hypotheses related to explaining Fitts' law include intermittent feedback hypothesis, impulse timing hypothesis, and multiples of movements hypothesis. Intermittent feedback hypothesis states that open-loop control is involved in the initiation of a rapid manual aiming task, but as the arm moves toward the target, the person intermittently uses feedback to generate sub-movements, small corrections in the trajectory, until the target is contacted. As the number of corrections increases, movement time amount increases for longer distances or narrower targets. Impulse timing hypothesis states that many speed accuracy tasks involve movements that are too fast to allow for the use of visual feedback to make corrections during the movement. Commands are programmed in advance of movement initiation. These commands are forwarded to the muscles as impulses, which are the forces produced during a specific amount of time. The result is that the arm is forcefully driven toward the target and achieves accuracy based on the specified amount of force and time. Multiples of movements hypothesis adopts elements of both hypotheses, intermittent feedback and impulse timing hypothesis. It proposes that before initiating movement, the person programs an initial impulse, which is then executed. If the movement is accurate, nothing further is required. But if feedback during the movement indicates that the movement will be inaccurate, the person prepares and executes sub-movements that adjust the initial velocity. This process continues until the person produces an accurate movement. When we consider the involvement of our sensory perceptual systems in the performance of a speed accuracy skill, vision plays an important role in enabling successful performance. There are three phases involved in the role of visual information in the speed accuracy trade-off: Phase 1, movement preparation, Phase 2, initial flight phase, and Phase 3, termination phase. The movement preparation phase begins when the person makes the decision to perform the skill involving a speed accuracy trade-off. In this phase, the person uses vision to determine the regulatory conditions that characterize the environmental context in which the action will occur. Initial flight phase is the first movement phase. It includes the beginning of the limb movement in the direction of the target. This movement is relatively fast, that is, ballistic, and occurs without the influence of sensory feedback, that is, open-loop control. The role of vision is very minimal in this phase. The termination phase begins just before and ends when the target is hit. Vision of the limb and target are important in this phase. The movement accuracy information must be transmitted to the central nervous system, and any needed movement corrections then occur to allow the person to achieve the action goal of hitting the target. Think about the way vision and movement interact in skills involving a speed-accuracy trade-off. The intended action influences the way in which vision functions. Prehension. Prehension is defined as the action of reaching for and grasping of objects. Prehension has three distinct components: transport, grasp, and object manipulation. Transport and grasp are temporally coupled and interact synergistically, or cooperatively, according to task demands. Basically, although the reach and the grasp are two separate movement components, they function in an interdependent manner. Object manipulation is defined as the functional goal for the prehension action. An important part of understanding the control of prehension relates to what the person intends to do with the object after grasping it. Prehension actions are a type of speed-accuracy skill because accurate hand movement is required and the movement speed will be influenced by that accuracy demand. The role of vision in the control of prehension skills is similar to that of speed-accuracy skills, except that visual feedback influences the grasp component according to the grasp and object manipulation requirements of the intended use of the object. Handwriting demonstrates an important motor control characteristic known as motor equivalence. Motor equivalence is defined as the capability of the motor control system to enable a person to achieve an action goal in a variety of situations and conditions. Vision performs two distinct functions in the control of handwriting: control of the overall spatial arrangement of words on a horizontal line and the production of accurate handwriting patterns, that is, the appropriate strokes and letters required for the written material. Bimanual coordination is defined as a motor skill that requires the simultaneous use of the two arms. There is either symmetric bimanual coordination or asymmetric bimanual coordination. Symmetric bimanual coordination is defined as two limbs doing the same thing, such as when a person in a wheelchair rolls the wheels of the chair in order to go straight forward or backward. Asymmetric bimanual coordination is defined as each limb doing something different. For example, a guitar player holds strings with one hand to determine chords, while plucking or striking strings with the other hand to produce sound. Locomotion, also referred to as gait, is defined by the rhythmic relationships that exist between step cycle components, arm and leg movements, and the movement of the pelvis and thorax. In order to understand the rhythmic structure of locomotion, one must consider higher-level nervous system involvement, musculoskeletal dynamics and environmental interactions. Catching a moving object versus striking a moving object. Catching a moving object occurs in three phases. To catch an object, the person must first move the arm and hand toward the oncoming object. Then, he or she must shape the hand to catch the object. In the last phase, the fingers must grasp the object. Similar to the action of catching a moving object, striking a moving object involves the spatial and temporal interception of an object. The motor control of this action involves the coordination of movements that is influenced by vision in particular ways. It is related to the influence of vision on the initiation of the striking movements and the compensatory adjustments to the initiated movements. What did we learn? Our understanding of the control processes underlying the performance of motor skills comes from research evidence. This evidence has identified specific performance characteristics associated with different types of skills. Speed accuracy skills, which require a person to produce movement that is both fast and accurate, typically demonstrate a speed-accuracy trade-off. That is, if the movement must be as accurate as possible, people move at a slower rate of speed than when accuracy is not important. Fitts' law provides a mathematical basis for predicting this trade-off on the basis of the task's movement distance and target size characteristics. Performance of prehension skills, which involve the reaching for and grasping of objects, demonstrates the temporal coupling of movement components that allow a person to achieve an action goal in different situations. The transport and grasp components function interdependently by adjusting certain movement kinematics. These movements adapt to specific characteristics of the object to be grasped and the manipulation goal of the prehensive action. Prehension movement kinematics, on the other hand, vary during both the transport and the grasp phases as a function of what the performer intends to do with the object after it is grasped. The role of vision in the control of prehension skills is similar to that of speed accuracy skills, except that visual feedback influences the grasp component according to the grasp and object manipulation requirements of the intended use of the object. Handwriting demonstrates an important motor control characteristic known as motor equivalence. A person can achieve the same action goal in a variety of situations that require movement adaptations dictated by the environmental context or by task characteristics. Bimanual coordination skills require the performance of both arms at the same time. Some tasks require symmetric bimanual coordination, that is, both arms perform in the same way at the same time. Others require asymmetric bimanual coordination, that is, each arm performs differently. Locomotion is defined by the rhythmic relationships that exist between step cycle components, arm and leg movements, and the movement of the pelvis and thorax. The catching of moving objects involves control processes similar to those for prehension actions, except that catching involves intercepting a moving object and the grasping of the object ends the action. Catching involves three distinct movement phases: moving the arm and hand toward the oncoming object, shaping the hand to catch the object, and using the fingers to grasp the object. The involvement of vision in the control of striking a moving object relates to the influence of vision on the initiation of the striking movements and the compensatory adjustments to the initiated movements.